Hi, welcome to the course General Chemistry 1A. This is a tutorial for the chapter Intermolecular Attractions and the Properties of Liquids and Solids.
Let's take a look at this question about cadmium sulfide. Cadmium sulfide is widely used in coloring pigments, semiconductor, photoluminescence, photoresistor, and solar cell. And there is a beta cadmium sulfide solid which has a crystalline structure of sphalerite, which is a structure similar to zinc blende with this, which is zinc sulfide. Now, the structure of this beta cadmium sulfide is as the following. So we have the red ball over here, which is the sulfide ion, and we have the smaller cation over here, which is cadmium 2+. And then there's an information over here which says that the sulfide ions reside in the corners and at the center. So in the corners and at the center of each face of the crystal lattice, while the cadmium 2+ ions reside inside the crystal lattice. Now for the question A, determine the number of each cadmium 2+ ion and sulfide ion in one unit cell of beta cadmium sulfide crystalline structure. So, for example, for the cadmium 2+, we are going to count the green small cation which reside inside the unit cell. So the cadmium 2+, it resides inside the unit cell. And if we calculate this based on the unit cell, so the green one here, 1, and then the next one over here, 2, and then the other one here, 3, and this one here, 4. So in total, we have 4 ions. And then if we take a look at the red ball, because we want to calculate the sulfide. Now, sulfide ion has two different places. So the first one is the corners. So there are some in the corner, and there are some in which reside at the center of each face. Now, for the one in the corners, we know that a cubic has 8 corners. And then, for example, if we take here, the one in the corner over here, we know that an atom or ion which resides in the corner of a cubic is shared between 8 other cubics. So in that case, for one unit cell, the portion is only 1/8, so 1/8, but we have 8 corners, so multiply by 8, so we have in total 1 ion, while for the one in the center of each face, so the one in the center, for example, let's take a look at this one. We know that the number of faces in one cubic, there are 6, and for the atom or ion which resides on the face of a cubic, it is shared between 2 cubics. So in that case, we are going to calculate, so we have like half, calculate that half, and then there are 6 faces in one cubic. So here we have 3 ions. So in total, the sulfide ion has 4. So in one unit cell, there are 4 ions of S2-. Now for the question B, determine the coordination number for each cadmium 2+ ion and S2- ion in the beta cadmium sulfide crystalline structure. Now what is the coordination number? So we are going to calculate how many atoms or ions surrounding a certain or a particular ions or atom with the closest distance. So for example, if we want to know the coordination number for the cadmium ion, so we are going to take, let's take one example. So for example, over here, the cadmium over here, we see that this cadmium over here is actually surrounded by 4 S2 minus. So this one over here, and then this one, and then this one, and also this one. The coordination number for cadmium 2 plus is 4. And then the next one is determining the coordination number of S2 minus ion. So we are going to calculate how many ions which surround the S2 minus ion with the closest distance. So for example, let's take a look at S2 minus. So for example, let's take a look at the S2 minus. So for example, this one. Now, if we see, based on this structure, if we imagine if there is like another cube over here, something like this, we know that there is also, like for example here, over here, the green one, which is cadmium 2 plus, and then there is also over here, so we have like this one. So in total, this sulfide will be surrounded by 4 cadmium 2 plus, which is this one over here, this one over here, this one over here, this one over here. So in that case, the coordination number for the S2 minus is also 4. So 1 CD2 plus is surrounded by 4 S2 minus ion. And then the other one over here, 1 S2 minus is surrounded by 4 CD2 plus ions. Now the next one, question C. The ionic radius of S2 minus is 184 picometer, and using assumption, this is very important information, that this calculation is based on the assumption. Let's highlight this one. Using assumption that S2 minus ions intersect on the diagonal of the face of the cube, so diagonal of the cube, calculate the length of the edge of the cube, which is A. So if we see here, this is the value that we want to look for, the A, which is the length of the edge of the cube of the beta cadmium sulfide crystal lattice in picometer. So there's a schematic picture over here, which will help us. So what should we understand? The first information is that the S2 minus ions intersect on the diagonal of the face of the cube. So meaning that if we take one face of the cube, so let's take one face. If we take one face of the cube, we know that the S2 minus resides in the corner of the cube, and then also on the center of the face. So if we take one face of the cube, like this one over here, this one is the one in the corner, which is shared by the other, which is shared among 8 cubes, and then this one over here is the one in the center. So have this, so this one is the one in the center, while this one is the one in the corner. Now, because there is an assumption that it intersects on the diagonal of the face, so if we have, for example, here we have the data of the length of the edge of the cube, which is A, and we take one face of the cube, and we know that we can take the Pythagoras formula. So if we have a triangle, over here,
something like this, and then this is the length of the edge of the cube, and this is the length of the edge of the cube. We know that this one should be a square root of 2, and we also know that from the information that the sulfide ion intersect on this diagonal of the face, we know that the length of the diagonal, which is a multiplied by the square root of 2, should be equals to r. This one over here, this is r, this is also r, so r plus this one over here should be this one over here should be 2r, so r plus 2r plus r, which is 4r. Now from this information, then we can write down the formula of the A, which is the length of the edge of the cube, which is 4r, then divided by the square root of 2. And in this case, this is 4, and then there's an information about the radius of S2 minus over here, which is 184 picometer, and then divided by the square root of 2. So here we have the value 520.43 picometer. Now the next question, calculate the density of beta cadmium sulfide in gram per centimeter cubic. Now to calculate the density in gram per centimeter cubic, so gram is a mass and then centimeter cubic is the volume. So we have the general formula to calculate the density, which is mass divided by volume. So what kind of mass? So specifically, this should be the mass of 1 unit cell divided by the volume of 1 unit cell. This should be mass of 1 unit cell and then divided by the volume of 1 unit cell. Remember that in this case, the form of the unit cell is a cube. So if we know the length of the edge of the cube, which is a, then the volume is a to the power of 3. So in that case, what is the mass of 1 unit cell? Now we know that in 1 unit cell there are 4 cadmium 2 plus, and then there are 4 S2 minus. So mass of 1 unit cell should be 4 multiplied by mass of 1 CD2 plus ion plus 4 multiplied by mass of 1 S2 minus ion, and then the volume, because this is the volume of the cube, and if we know the length of the edge of the cube, then the volume should be a to the power of 3. Now, how do we calculate mass of 1 cadmium 2 plus? Remember that whether it is atom or ion, we know that there is an information of atomic mass or the molar mass. So for example, we know the molar mass of cadmium. Now, the molar mass, for example, molar mass of cadmium, that should be, the unit should be in gram per mole. So we have the mass of 1 mole of cadmium. Now, what is the mass of 1 cadmium? Then the calculation should be, if you want to know, mass of 1 CD, then it should be the molar mass divided by the Avogadro number, because we know that in 1 mole there is an Avogadro number of cadmium ions in this case. By that approach, now we can calculate the density over here. So density should be 4, and then mass of 1 cadmium 2 plus, we calculated from the molar mass of cadmium 2 plus, or the atomic mass, we can say that, CD2 plus, and then divided by the Avogadro number, and then mass of 1 S2 minus is the molar mass of S2 minus divided by the Avogadro number, and then the total of this the total of the mass of one unit cell divided by the volume of the cube of one unit cell, which is A to the power of 3. Now, if we see over here, if we see this one here and here, we can simplify the formula. So here we have 4 per L, and then we have this one, CD. 2 plus the atomic mass of S2 minus over here, and then divided by the volume. Now, if we see this one, the total of the atomic mass of CD2 plus S2 minus is actually the molar mass of CDS. So if we know the molar mass of CDS, then we can simplify this, so something like this. So we have 4 per L. L is Avogadro number for molar mass of CDS, and then divided by the volume. Now, the formula mass of the cadmium sulfide over here, and then for the sulfide 32.06. So we have here gram per mole. So now the density is 4.4447, and then it is divided by L and then by the volume. Now we should consider the unit, because here the unit should be in centimeter cubic. So we can, for example, here we can change the picometer to centimeter. Okay, so we calculate the volume in centimeter cubic. So A in centimeter, which is 520.43, something like this. Just this one. So the density is around 6.81 gram per centimeter cubic. Now the question E. It is known that the density of a pure beta cyclodextrin crystal is 4.87 gram per centimeter cubic, which is less than the one we calculated before. Explain why the density calculated in D is different compared to this data. Okay, so the calculation in the question D is using a value based on assumption that 3 S2 minus ions intersect at the diagonal of the face of the cube, which is not possible. I mean, if we see this one over here, when there are 3 ions residing close to each other, that's impossible because there should be repulsion between these ions. So this assumption is actually not correct. So that's why our calculation is not in agreement with the experimental data.